So in this lecture, I'm going to show you different problem sets that you could be getting for solution stoichiometry or limiting excess reactant or a combination of limiting excess type of problems in solution. So let's look at question number 1. What mass of precipitate is formed if 12.4 milliliters of a 1.25 molar ammonium phosphate solution is added to a solution containing excess iron 2 sulfate? So let's first write the equation here. So you have a reaction of ammonium phosphate. So we write the reaction for ammonium phosphate. So we have a solution of ammonium phosphate and iron 2 sulfate. This is a double displacement reaction. You would expect iron 2 phosphate, which is a solid, and ammonium sulfate. So the precipitate here is iron 2 phosphate. Now we gotta make sure that the reaction is balanced first. Now let's see what's given to us. We have 12.4 milliliters of a 1.25 molar ammonium phosphate. So we have 12.4 milliliters, which is 1.25 molar. And we want to know how much of the precipitate in grams would be formed if we have enough of iron 2 sulfate. So this is the stoichiometry reaction. In order to find the mass of our precipitate, we need to know the number of moles of precipitate that we'll be producing in this reaction. So we're gonna need to do a mole to mole ratio here to find out how many moles of iron 2 phosphate will be produced. So our plan here is from molarity and volume of ammonium phosphate, we want to find the number of moles of ammonium phosphate. Once we have moles of ammonium phosphate based on the balance equation, we want to find moles of iron 2 phosphate. And once we have moles of iron 2 phosphate, we're going to use the molar mass of iron 2 phosphate, and we can find the mass of iron 2 phosphate. So let's start. Our solution is 1.25 molar. So we have 1.25 moles of ammonium phosphate per 1 liter of solution of ammonium phosphate. Now to get the number of moles, we need to multiply this by the volume of ammonium phosphate. Now your ammonium phosphate is 12.4 milliliters, but we need to convert this to liters. So 0.0124 liters of ammonium phosphate. So liters and liters cancel out. So we have the moles of ammonium phosphate. Now to convert to moles of iron 2 phosphate, so there is a 2 here. Yeah. So to convert to moles, you look at the balanced reaction. Each 2 moles of ammonium phosphate produces 1 mole of iron 2 phosphate. Now to convert this to mass, we know that each mole of iron 2 phosphate is 357.49 grams. So from here, you would expect 2.77 grams of iron 2 phosphate. So let's look at another example here. A total of 40 milliliters of 0.55 molar copper 2 sulfate solution is added to a beaker containing 2.02 grams of zinc. What is the limiting reactant? How much copper is recovered from solution, and how much excess in grams remains of the other reactant? So first of all, let's write the equation. So we're looking at a single displacement reaction of zinc and copper 2 sulfate. So from this reaction, we would expect copper metal and zinc sulfate. And the reaction is balanced. So now let's see what's given to us. We have a total of 40 milliliters of 0.55 molar copper 2 sulfate. So we have 40 milliliters of 0.55 molar copper 2 sulfate solution, and we add this to 2.02 grams of zinc. Now we want to know first of all what's the limiting reactant. So to find the limiting reactant from the molarity and volume of copper 2 sulfate, I'm going to find moles of copper 2 sulfate, and then I'm going to find moles of copper. And I'm going to do the same thing with zinc too. So from mass of zinc, I'm going to find moles of zinc and then moles of copper. Once I find moles of copper from these two calculations, I'm going to compare them in order to identify if zinc or copper 2 sulfate are my limiting reactants. So let's start with copper 2 sulfate. We have 0.55 molar. And we have 40 milliliters of this, which needs to be converted to liters. So liter and liter cancel out. Now based on the balanced reaction, each mole of copper 2 sulfate produces 1 mole of copper. So from here, I would expect 0.022 moles of copper. So what this means is that if all 40 milliliters of 0.55 molar copper 2 sulfate is consumed, I would expect to get 0.022 moles of copper. Now, let's assume if the entire 2.02 grams of zinc is consumed, how much copper would be produced? So we're going to convert this to moles of zinc first. Now based on the balanced reaction, each mole zinc produces 1 mole of copper, and from here we would expect 0.0309 moles of copper. Now if you compare these two together, this tells me that basically copper 2 sulfate is the limiting reactant. So the maximum amount of copper that could be produced is 0.022 moles. So we answered the first question, which was the limiting reactant. Now second part is asking how much copper is recovered from the solution. So since copper 2 sulfate is the limiting reactant, the maximum amount of copper we can recover from this reaction is 0.022 moles. So we can convert that to grams. So 0.022 moles of copper. To convert it to mass, we're gonna have to use the molar mass of copper. So 1 more copper, 63.55 grams of copper. And from here you would expect 1.4 grams of copper. So last part is asking how much excess remains of the other reactant. So our excess reactant here is zinc. So we have 2.02 grams of zinc. In order to see how much excess is remained, we first need to know how much of the zinc actually reacted with our copper 2 sulfate solution. So the first step is finding out how much of the zinc reacted with copper 2 sulfate solution. So what I'm gonna do here is that I'm going to do a mole-to-mole ratio between copper 2 sulfate and zinc and see how much zinc I need for 40 milliliters of 0.55 molar copper 2 sulfate solution. So from molarity of copper 2 sulfate, I'm going to find moles of copper 2 sulfate, and then I'm going to find moles of zinc that reacts with copper 2 sulfate, and from there I'm going to find the mass of zinc. And this is going to be the mass of zinc that basically reacts with the copper 2 sulfate solution. So we have a 0.55 molar copper 2 sulfate solution. So to convert it to moles, we multiply by the volume of copper 2 sulfate solution. Now, based on the balance reaction, each mole copper 2 sulfate reacts with 1 mole of zinc. And now each mole zinc is 65.39 grams of zinc. So from here we said 1.4 grams of zinc reacted. So what this tells me is that out of that 2.02 grams of zinc, only 1.4 grams reacted. So how much is left? We started with 2.02 grams of zinc. Out of that, we know that only 1.4 grams of zinc reacts. That means we have 0.6 grams of zinc which remains, or we can also say is unreacted. So let's look at another question here. What volume of 0.90 molar sodium carbonate solution must be added to excess 1.5 molar calcium chloride solution in order to form 12.2 grams of precipitate? So let's first write the equation and then we see what's given to us and what we're solving for. So here we're looking at a reaction of calcium chloride and sodium carbonate. So double replacement reaction, you would expect calcium carbonate and sodium chloride. So we want to know what volume of sodium carbonate, which is a 0.90 molar, must be added to excess 1.5 molar calcium chloride, and by doing this we want to end up having only 12.2 grams of precipitate, which is calcium carbonate. So the mass of calcium carbonate is giving to us. So in order to do this, we have to do a mole-to-mole ratio. So we want to go from the desired mass, which is the mass of calcium carbonate, see how many moles is that 12.2 grams of calcium carbonate, and then based on the balanced reaction we want to find the moles of sodium carbonate needed. And once we find the moles of sodium carbonate based on the molarity, we're going to find volume of sodium carbonate solution that's needed. So let's start with 12.2 grams of calcium carbonate. We're going to convert this to moles, so each mole of calcium carbonate is 100.09 grams of calcium carbonate. Now based on the balanced reaction, each mole calcium carbonate is produced from a reaction of 1 mole sodium carbonate. And then in order to find the volume, we know that our sodium carbonate solution is a 0.9 molar, so 0.9 moles of sodium carbonate per 1 liter of sodium carbonate. So this cancels out and we should end up only with volume of sodium carbonate. So this is going to be 0.136 liters of sodium carbonate. In order to find the volume in milliliters, you multiply it by 1,000 and that would be 136 milliliters of sodium carbonate.